Yep, that's working. So my talk is going to be based on a paper with the same title that's joined with Josh Anglis, Duskanarita, and Parag Patak. We have already seen in All and Parag's talk that market design offers practical solutions for real-life allocation problems with appealing properties such as strategy proofness, efficiency, and fairness. In addition to these economic considerations, centralized assignment also generates valuable data for empirical research, especially in the context of school choice. In particular, when schools are oversubscribed, lottery-based rationing of seats at schools creates a quasi-experimental variation in student assignment that can be used for credible evaluation of individual schools and school models, school reform models such as charters. However, market design solutions like deferred acceptance bury such randomized trials into a complex information structure on student preferences and priorities. Yet, as all claimed, rules are data, and knowing the rules are going to help us to fully exploit such randomized experiments from the data. And the bulk of my talk today is going to focus on that. I am going to show first how to fully exploit quasi-experimental variation in a deferred acceptance-like mechanisms. And we are going to propose a method for research design. And we are going to use Denver's public schools as our test bed. We are going to study the charter schools and other alternative school sectors, and we are going to use the deferred acceptance generated offers to compute the two-stage least squares estimates of the causal effect of attending charter schools and attendance in other sectors. I'm also going to compare our method with alternative methods. So let's start then. Let's consider a school choice program that assigns students to schools via a deferred acceptance mechanism. Let DIS denote whether student I gets an offer from school S or not. Now, any applicant that goes to the deferred acceptance has to submit a preference list and also has priorities that may be determined by family income or neighborhood. Now, we are going to refer to an applicant's preferences and priorities as his or her type. As you have seen in All and Parag's notes, the offers are determined by the distribution of types and potentially by random numbers in deferred acceptance and potentially in other market design solutions. Yet, those types are far from being random. For example, families tend to locate into neighborhoods depending on family income, school quality, motivation, etc. Therefore, types are likely to be correlated with outcomes, creating a source for omitted variable bias. And the question boils down to how to eliminate that omitted variable bias. Now, under deferred acceptance, if two students have the same types, basically the same preference lists and same priorities, and if the priorities are thick, deferred acceptance uses lotteries to break ties among such kids. Consequently, students with the same types are assigned the schools in the choice lists with the same probability. That implies that the A with random tiebreaker actually induces a stratified randomized control trial. In particular, for any random variable Wi, that is independent of the lottery numbers, the probability of being assigned school S, conditional on type, is independent of Wi. Wi may include potential outcomes and student characteristics like sibling and free lunch status. This immediately gives us a straightforward research design. Conditioning on type, we can actually eliminate the omitted variable bias in comparisons by offer status. Yet this turns out to be impractical in the data. For instance, because such conditioning creates just too many cells with very few students within, and usually with no variation in offers within the cells. In particular, in Denver, about 5,000 charter applicants include more than 4,300 distinct types, eliminating many of the schools and students from the study. Instead, we are going to condition on the propensity score. The propensity score is the probability of assignment to school S for a given type. The conditional independence result on the previous slide implies that conditional on the propensity score, offers are going to be independent of any random variable that's independent of lottery numbers. In particular, offers are going to be independent of potential outcomes conditional on propensity score. That turns out to be useful because score is going to be much coarser than type, and it's also going to identify the full set of applicants for whom we have a randomized school assignment experiment. Now, let's see how this works in a simple example. In this example, we have 5 students, 1, 2, 3, 4, 5, and 3 schools, A, B, C, each with 1 seat. Student preferences are given as follows. Student 1's first choice is A. His second choice is B. Student 3 ranks only school A. Student 2 has priority at B, and 5 has priority at C. 1 and 2 have the same preferences, but they are not the same type because they have different priorities. In fact, here, types are unique. Type conditioning creates 5 cells with 1 student in each, eliminating a potential research design. Now let's look at the deferred acceptance. By virtue of high priority, 5 is going to get C. Then 1, 2, 3, and 4 are going to be considered for assignment at A, with no one advantage there. Consequently, deferred acceptance is going to assign school A to one of those 4 students with equal probability of 0.25. So conditioning on the propensity score, we are going to create one big cell with 4 students in it and offer variation. Now, the deferred acceptance propensity score is actually a permutation distribution. It is a relative frequency of assignments generated by all possible lotteries. In our Denver case, there are about 11,000 students. So one would need to run the deferred acceptance algorithm with all 11,000 factorial lotteries to compute the actual propensity score. This is a technically impossible task at the moment. However, a conventional law of large numbers suggests that it is actually enough to sample lottery numbers. Yet, since the types are discrete, the empirical distribution, the score distribution, turns out to have, it usually has at most as many points as the support theta does. So it does not offer further dimension reduction. Therefore, one would need to rely on smoothing the propensity score in order to get further dimension reduction. Simulation scores also kind of a black box. They are also kind of a black box. They don't say much about what's going on with the randomized trials in the data. If we had some kind of formula for the score, we could have said something about what is going on with such experiments. Yet, in general, propensity score does not have a closed form solution. Alternatively, we are going to develop an asymptotic large market approximation to the finite economy score. The DA score for a continuum market is going to achieve a couple of things. First, it's going to approximate the propensity score as a function of a few easily computed statistics. It's going to be caused automatically, so we are not going to need any smoothing. It's also going to reveal the nature of the stratified trial embedded in deferred acceptance. In particular, it's going to tell us which schools have random assignments and why. Now, to this end, we are going to first characterize the deferred acceptance via admissions cutoffs. As it has been done by others earlier in the literature, given a set of students and schools and their priorities and preferences, I am first going to define a student's rank at school S. Student I's rank at school S is going to be the sum of his priority at school S plus his random number. And students are going to be ranked according to this rank. The lower this number, the higher the student is in the ranking. Priorities are going to take integer values, and the random numbers are going to take values between 0 and 1. Therefore, the ranks, student ranks, are going to be lexicographic in priorities and random numbers. Now, the admissions cutoff at a school is going to be determined by the rank of the lowest student that gets an offer from the school under DA. Given those cutoffs, a set of cutoffs, then it's going to be easy to determine who gets a DA offer or not. In particular, student I is going to be assigned school S if I rank school somewhere in his or her choice list, plus his rank is better than the admissions cutoff at school S, plus his rank is strictly worse than the admissions cutoff at any school he prefers to S. And I is going to be assigned if and only if this condition holds. Let's see what this means. Here is a bunch of students applying to school S. Each row represents a student. The first student has priority 1 and the random number 0.13. His rank is 1.13. The second student has priority number 1, random number 0.99, and her rank is 199. And students are listed according to their rank here. Some students get offers. The student that gets, the lowest rank student that gets the offer determines the cutoff at that school. In particular, the cutoff is given by 2.35 in this simple example. We are going to refer the integer part of that to as the marginal priority, and the decimal part, 0.35, as the lottery cutoff. Given that now, we are going to partition the set of types of the applicants to school S in some way. In particular, we are going to call those two students never seated students. Those students have priority of 3, which is worse than 2. Even if they got the best random number, they would not be offered a seat at that school. That's why we are going to call them never seated. The top 2 students are the ones that we are going to call always seated. Those students have priority 1, which is strictly better than the marginal priority. So whenever they are not offered a more preferred school, they are going to get an offer from this school. The remaining set of students are what we are going to call conditionally seated students. Conditionally seated students have priority that's equal to the marginal priority at that school, and the assignment among those students is actually determined by the random number. Now, given this partition, the next construct we are going to use is what we call most informative disqualification. Most informative disqualification, MID, tells us how the lottery number distributions for applicants to S is truncated by qualification at more preferred schools. Consider the first line. B theta S is the set of schools that type theta students prefer to school S. If in the first line the priority of the type theta student is worse than the cutoff, marginal priority of the more preferred schools for type theta students. When those students apply to those schools, they are not going to get an offer from those schools. Therefore, all those students are going to end up being considered for school S. By the time they apply to school S, their random numbers can take any value between 0 and 1, indicating no truncation. Therefore, MID is going to be equal to 0. In contrast, the types on the second row have priority that is strictly better than the marginal priority at some school they prefer to S. All of those students are going to get a better school, and none of them are going to apply to school S. Therefore, their random numbers are going to be fully truncated. MID equal to 1 is going to indicate that. For other students, those students are going to apply to S, and they are going to be considered for a seat at S only if they cannot clear the lottery cutoff at more preferred schools. And their MIDs are going to be characterized by the most forgiving cutoff at such schools. Given these constructs then, our first theorem gives us a simple formula of the deferred acceptance propensity score in the continuum economy. The MIDs, the cutoffs, lottery cutoffs, and the partition sets are population quantities. They are not random. They are going to be fixed in the continuum economy. Our second theorem shows that the sample analog of that score actually converges uniformly to the finite market score as market size grows. And this is what we are going to utilize next. So in order to compute the score, first we are going to use brute force simulations. We are going to do this. We are going to run the deferred acceptance by running it with 1 million lotteries. And we are going to compute the empirical assignment rate for each type. This, by law of large numbers, converges to the actual finite market score. Yet, we don't obtain much dimension reduction here. The simulated score identifies about 1,500 students that are subject to non-trivial charter assignment risk. That is, their proportion that about 1,500 students have a propensity score between 0 and 1. And there are more than 1,100 distinct score values. Alternatively, we are also going to use our theorem 1 to estimate the DA score. First, and we are going to do this in 2 ways. First, we are going to take the realized economy with the realized random numbers and assignments. We are going to compute the MIDs, lottery cutoffs, and we are going to sort students into priority statuses. And we are going to plug them into our formula. That's going to give us an estimate for the DA score. Second, we are going to use the empirical offer rates defined by this formula. And it turns out that the frequency is much closer to the finite score, and it's approximately unbiased. Now, given this, we are going to use the Denver public schools as a test bed to show how we can utilize propensity scores. Now, the Denver public schools is an interesting laboratory for impact evaluation because, first of all, it is majority Hispanic. About 60% of the students are Hispanic origin. And it has a large charter sector and other non-traditional sectors. And equally important, almost all of the schools are assigned through a unified centralized assignment. Consequently, we observe that the DPS charter applicants look very much like the rest of the district population. Now, in our benchmark model, we are going to study the impact of attending a charter school. And to this end, we are going to have an endogenous variable CI that indicates charter enrollment. Our instrument, any charter offer, is going to indicate whether a student gets an offer from a charter school that he or she ranks. And our key control is going to be the any charter propensity score. That is the probability of being assigned to a charter school. Now, we are also going to be interested in student outcomes 1 year later, like math and reading scores. And we are going to populate our 2-stage least square equations with the propensity score dummies. The DIX in particular is going to indicate score values, and the coefficients gamma and alpha are going to be the score effects. So in our study, we actually study charters at all grade levels, K to 12, and this table reports records the elementary and middle schools only. The first column, a yes in the first column, says that the corresponding school is managed by a charter management organization. Column number 1 reports the number of students who rank the corresponding school somewhere in their choice list. In particular, 324 students rank Stripe Prep GVR somewhere in their choice list. And the school makes offers to 112 of them. The simulated score identifies that 119 of them have non-trivial risk of assignment at that school. That is, their propensity score is strictly between 0 and 1. Alternatives, there are alternative strategies that have been adopted in the literature before. One of them is what we are going to call the first choice strategy. I'm going to come back to that. In short, a first choice strategy focuses on the set of students who rank a charter school as their first choice. The last column actually reports the number of students who rank a charter school as their first choice and who are subject to non-trivial charter assignment at that school. And in this case, actually, we observe that no students who rank this school as their first choice are subject to random assignment. Therefore, such strategies directly eliminate this school from a potential study and all those 119 students that are subject to some non-trivial risk. Now, let me skip this one. Let me go into, let us take a close look at those schools and let us see what's happening. This table lists the Stripe prep schools, and the first column shows the number of eligible applicants that rank these schools somewhere in their choice list. And the second column reports the number of capacities, and the third column reports the number of offers. Notice that the first 4 schools are actually making fewer offers than seats available at those schools. So a naive definition of oversubscription based on the number of offers and capacities would probably tend to eliminate those schools from any research design. But we have already seen that many students are subject to non-trivial charter assignment at those schools. So what's going on here? Well, the column 6 shows that no conditionally seated students are subject to random assignment at those 4 schools. And table 8, the column 8 shows that those who are subject to random assignment are always seated types. That is, those students are assigned to those schools not because they fail to qualify for an assignment at that school, but they fail to qualify for assignment at a school they prefer more. By the time they lose the lottery at a more preferred school, they come back to these schools and they are assigned. And in contrast, the last school, Westwood, actually, all of the randomization occurs among the set of conditionally seated students. These are the students that have priority equal to the marginal priority, and the assignment among those students is determined by random lottery at that school. So the cutoff of that school is going to determine the admissions at that school. Now, given that, let's take a quick look at the DPS students again. As we mentioned, it is majority that the first column reports average characteristics of the whole population, DPS population. The DPS students tend to be majority Hispanic, and the baseline scores are standardized to mean 0 standard deviation for the whole population. And the third column reports the same averages for charter applicants only. And as apparent from here, the baseline scores for charter applicants look very much like the rest of the population, indicating much less positive selection into charter lotteries than, for instance, the Boston charters. Now, so given that this table reports 2-stage least square estimates of our benchmark model by using 3 different estimates of the propensity score. The first column uses the frequency, the second column uses the formula, and the third column uses the simulated scores. The first stage indicates that a charter offer actually bumps the charter enrollment rates by 0.45. That number takes into account the population of students who are referred as always takers in the late framework. Those students constitute about 43% of the whole population. They do not get an offer in the first round, but charter offer in the first round, but somehow find a way to get into a charter school in later rounds. The second, the two-stage least square estimates actually show remarkably large gains for math, and these are similar to those reported for Boston charters. Like in earlier ladder-based charter studies, we also find a positive but relatively smaller impact gains for reading. We also find large gains for writing. For equally important though, for the purpose of our methodological agenda, check out the numbers on those three columns. The estimates are actually pretty close to each other, indicating that our asymptotic large market approximation is doing pretty well in eliminating the selection bias. So the Denver Public Schools is actually an interesting mix of schools. There are charter schools that are managed by CMOs. There are charter schools that run independently. There are traditional schools. There are other non-traditional schools, such as innovation schools. Innovation schools, for instance, run under an innovation plan that waives some provisions of the relevant collective bargaining agreement. Our two-stage least square estimates estimate an average causal effect for a particular set of students, which we are going to refer as compliers within the late framework. Compliers are the set of students who enroll at charter school only when they get an offer from a charter school, but not otherwise. We cannot necessarily say who is a complier or not, but we can estimate some outcomes for those students using Abadi's methodology. In fact, this table tells us what compliers would do when they get an offer and when they don't get an offer. The top panel shows that the compliers who get a charter offer, 95% of them end up at a CMO charter, and the remaining 5% ends up at a non-CMO charter. The lower panel shows that compliers that do not get an offer, only about 39% of them end up at a traditional public school. Surprisingly, about 42% of them end up in an innovation school. These observations actually motivate a more elaborate model in order to isolate school sector effects. Doing so actually is going to allow us to distinguish within charter sectors. It will also turn the non-charter counterfactual into one of mostly traditional public schools. And to this end, we are going to employ a two-stage least square strategy with 3 endogenous variables and 3 offer dummies. Each endogenous variable is going to indicate enrollment in a corresponding sector, and we are going to focus on CMO charters, non-CMO charters, and innovation sector. And each endogenous variable is going to indicate enrollment in a corresponding sector. And the offer dummies are going to indicate getting an offer from a corresponding sector. And we are going to saturate our two-stage least square equations by propensity scores that are the probability of getting an offer from a particular sector. Given this model, this table reports multiple estimates. The left-hand side actually studies the single sectors. The first column focuses on the CMO schools and applicants that apply to CMO charters. The second column studies applicants that apply to non-CMO charters. And the third column considers only innovation school applicants, and the students who apply to innovation schools. Well, the first stages are all significant, and this two-stage least square estimates show a remarkably large gain for the CMO schools as before. The non-CMO schools show statistically insignificant yet a negative impact, and the innovation schools, on the other hand, show a marginally significant and negative impact. Recall that, for example, in this column, in column 3, a non-innovation counterfactual includes all of the charter schools. Our multi-sector model actually tries to isolate all those sectors independently. When we estimate this model in the third column, the third column shows that, after isolating those sector effects, the third column shows large gains, very large gains for the CMO charters, and almost non-existent gains for non-CMOs. And interestingly, the marginally significant negative impact turns into an insignificant positive impact after taking out the charter schools from the non-innovation counterfactual. And the estimates are pretty similar when we use the joint controls as well. We don't need to use joint controls, but when we do it, we obtain the similar results. So we have already seen, kind of demonstrated the power of this conditioning and propensity score. Now, next, let us try to compare this to the alternative strategies adopted by other people in the previous literature. One of them is what we are going to call the first choice strategy. First choice strategy focuses on the set of students who rank a charter school as their first choice. In that specification, our theta is going to identify the charter school student I ranks along with his priority. And the first choice instrument, the DFI, is going to indicate qualification at the first choice. That's whether a student's rank is better than the admissions cutoff at that school or not. Now, given that the first choice strategy is going to saturate the two-stage least square equations by the dummies that indicate the values for Ri. Obviously, this strategy discards a lot of information since it does not consider charter schools that are ranked lower than the first choice. Alternatively, a qualification instrument considers all of the charter schools that is ranked by a student. The Ri becomes the set of all charter schools that I ranks along with his priorities at that school. And the qualification dummy indicates I's qualification at any charter he or she has ranked. And the specification is similar. The next table actually reports the two-stage least square estimates from those three different strategies. The first column is what we have seen before. This is our any charter approach. The second column reports estimates from the first choice strategy. And the third one is the qualification strategy. The first row here reports coefficients from regressing our any charter dummy on alternatives. In particular, the first choice dummy is capable of explaining only about 73% of the offers from any charter. Also, the estimates show remarkably larger gains for first choice schools. Now, check out the set of number of schools that are included in these studies. While our any charter offer can study 32 schools, a first choice approach can study only 18 schools. Given this fact, then obtaining a higher gains for the first choice strategy probably is not too surprising, because the first choice strategy focuses on a specific set of schools. Probably parents tend to rank higher achieving schools higher in their choices. This result might be the fact of that, but there's also a debate in the literature that focuses on the advantage of getting an offer from a first choice. We can actually address this heads-on in with our methodology. We can use the same multi-sector model to study to isolate the impact of attending a first choice charter versus other choice charters. Column 1 actually shows that there is a significant gain from attending a first choice charter relative to attending other choice charters. We can actually take this one step further and try to isolate the effect of different charter models. And that is what the second column is doing. The second column is isolating the effect of first choice charters, other choice charters, along with CMO charters and non-CMO charters. And those numbers, the first two numbers in column 2, indicate that most of the advantages from attending a first choice charter is collected if the first choice charter is a CMO. The method we developed, although we have discussed only deferred acceptance mechanisms, the method we have developed applies to the variants of deferred acceptance mechanisms easily, such as the random serial dictatorship and Boston's immediate acceptance mechanism. There's actually a growing literature that utilizes centralized assignment, and we hope that there's going to be even more research that uses the data from centralized assignment, mainly because more and more school districts are moving to centralized assignment. And the results we show indicate that the methods we propose actually may allow more to be learned from these data. Now, there's a lot to be done with the centralized assignment data, both from an econometric theory point of view and applied. So the particular projects that excite us and that are in progress include exploiting randomized trials embedded in non-DA mechanisms like top-tiering cycles. Also, we are interested in designing mechanisms for impact evaluation. Recall that deferred acceptance relies on lotteries to break ties among equal priority kids. So how are we going to break those ties? Are we going to assign a single lottery number to each student, or are we going to throw a new lottery at each school? Which lottery, a single lottery or a multiple lottery, is better for research design? That's one question that we are interested in. Another question is actually to exploit the full power of the score in value-added model style research. One picture that I omitted actually shows that the similar sample size gains, significant size gains occur in charter schools, non-charter schools, traditional schools, pretty much all across the thing.